4.5%. When you go, click on the notch, 93. Look at this.
Hello, hello, hello.
You got 4.5. First. They match dollar for dollar. And then the next 3%, they match 50 cents. Yeah. I don't like that. Hold on. Half. 401k half drop. The 401k, the money goes in after tax. When you take out your 401k, you go for the so stay away around. 401k goes in before taxes. Take it out, it's tax. On a Roth IRA, you pay your taxes now, when you put it in there, so whatever your balance is, again, take it out. Oh, that makes sense. The other thing, the other interesting thing I did, if I have some money in the bank, I told them if the direct deposit, 90%. I put in two messages for one last year. There's been a really nice, I don't know if I want to do it, it's North Attleboro, right on Main Street, right above, like next door to, bank, north there. Cool, it's giant studio, nice hardwood floor, basically,
Okay, indoor voice.
13.50 a month. But I have to buy like a Murphy bag. I can check it out. I would have to buy, like if I spent $2 billion on a Murphy bag, say $2 billion.
Yeah.
Yeah, so that one I have to know about. Really like just like the area of the and the other side is a little better.
Stop it.
Yeah, I don't think it's for Like, in one little balls. This is the one. We come to that weird shape. Yeah. Second floor. Oh, it's only the back. Yeah. I was turned off. This one is itself. This one.
Yeah.
Second floor. Oh, the mile?
Progress.
Yeah, those are like $19, something green. Yeah, it's like still on Zillow.
Boom.
Yeah. those are nice.
Mhm.
So. Yeah.
On your phone, your pocket, you go there 8 hours every day, sit there 8 hours every day. So, 8 hours a day.
All right, looks like it's time to get rolling here.
Oh,
How's everybody doing?
fantastic.
Good. Yourself?
Good.
All right. All right, once again, it's my usual to remind you, if you're a second fireman, you need to launch your application. It needs to be on their desk this Friday if you plan on taking the test December 28th. All right, probably sick of hearing it. Everybody got it done that wants to get it done.
Yeah.
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 I got
All right.
confirmation on the email.
So that's that. And you won't hear from them. You won't hear from them until around December 10th. And they'll send you a letter telling you when to report. You know it's going to be on December 28th. Usually they tell you to show up at 8:30 in the morning. But that's that. I'll probably only bring that up a couple more times before we before we get there. All right. Next, last class you took the midterm. By now, everybody should have gotten the answers. Everybody's got a pretty good feel, I think, of how they did. All right. Remember, you only have to get a 70% on the state exam to have a passing grade. So I don't think anybody's in danger of either failing the course or failing the written test with the state. Did anybody have any specific questions about the midterm? Anybody unhappy with their grade? Because there is an 800 number I can give you where you can complain. Sometimes people feel better. But yeah, everybody did good. Everybody, I think, has got the drift of it. The questions are in the format that you'll see on the state exam. They're all multiple choice. And Most of these questions were taken right from the state database, so couple more of these and you'll be good to go. All right, shouldn't have any problem going down the road. All right, so we'll put the midterm to bed. All right. On tonight's agenda is combustion. That combustion section, hold on a minute, let me get back to the page here. Should be the next section in the book. And basically how it starts is with a bunch of definitions, just like every other section. All right, what you need to know about combustion. Combustion is something they taught you in 4th grade science. Everybody knows what it is. The way it's worded on the state exam is it's defined as a chemical process in which a combustible unites oxygen, producing heat and often light. All right. And the way that question's set up, they give you the definition with a blank in front of it. So all you really need to do is memorize the definition of combustion to answer that question correctly. Even if you looked it up in the dictionary, which says the rapid union or oxidation of an element or compound with oxygen that results in the production of heat, you'd get it right. So I don't care how you remember it, but they're going to ask you, what is combustion, or what is the definition of combustion? So you know that's coming your way. In the combustion world, in our actual day-to-day practice, I think everybody gets it, that combustion happens continuously in a boiler. All right. And in this day and age, it's automatically controlled. The only thing an operator has to do is periodically check, see how it's doing, make sure everything looks good. All right. Respond to any alarms. But for the most part, combustion happens in the background without our direct involvement. All right. But there are a couple things you need to know. All right. One of the reasons you're in the boiler room in the first place is to assure that we're getting complete combustion. All right. And that means, by the definition, complete combustion is burning the fuel completely using the minimum amount of excess air. All right. One of the things that they may ask about that you and I can't achieve is perfect combustion. Perfect combustion is defined as burning the fuel completely using only the theoretical amount of air. That's not possible. That's not going to happen for us. So the best you and I can do is complete combustion. All right. What happens when that goes wrong usually is what they call incomplete combustion. All right. That's when you're not burning all the fuel. Most times, this will result in smoke or visible emissions from the boiler. All right. All right. Anytime you see smoke, you're going to assume we have incomplete combustion. To me and you, that just means we don't have enough air. Right? All right. So we should make an adjustment, all right, to that fuel air ratio. For third engineers, the $5 word they're using today is stoichiometric combustion. Stoichiometric combustion is the same thing as perfect combustion. All right. Some of the low NOx burners that are out there today that they utilize on boilers utilize what they call stoichiometric combustion. All right. They admit the theoretical amount of air with the fuel to produce the least amount of NOx emissions. So it's a pretty common technology. It's a pretty common word in the industry. Very often they'll ask a third engineer, what is the definition of stoichiometric combustion? Same thing as perfect combustion. Everybody needs to know the definition of excess air. All right. And that's defined as the amount of air supplied to the combustion process that is greater than the theoretical amount required. Let me draw you a quick example so you get the feel for this. In most boiler operations, we are monitoring what comes out the stack. And what that usually means is that somewhere in the chimney, there's a probe. Goes to a flue gas analyzer, and what it's looking for is what's coming out the stack. All right. One of the key indicators for us as to what's going on in the furnace is the presence of oxygen here. If I had perfect combustion, if I admitted just the exact amount, the theoretical amount of air with the fuel, what do you think the O2 reading would be at the stack?
0.
It would be 0. Good. All right. Is it ever going to be 0?
No.
No, we can't get perfect combustion. So the O2 reading that we see, all right, is a direct indication of excess air. All right. The only thing you and I want to do is minimize that. The other components that we're likely to see are carbon dioxide, CO2, and carbon monoxide, CO. Right. Everybody kind of gets this. All right. Today, the number one criteria pollutant is what they call NOx, oxides of nitrogen. All right. NOx is the reason that all cars have catalytic converters on them. All right. All of these gases are invisible to you and I. Can't see them. All right. We know they're going out there, but we can't see them. All right. If you see black smoke, is that bad?
Yep.
Always bad. All right. If you're burning natural gas and you see black smoke, all right, you are seriously fuel rich. All right. What should be your first move?
There.
Add some air. There you go. All right. Open a register, a damper, whatever's gone wrong here. You need more air. So it's often pretty good, pretty simple to diagnose what's going on. All right. Just by looking at what's coming out the stack. All right. So the question they're going to ask you on the state exam is excess air necessary? And what are they looking for?
Yes.
Yes. Yeah. All right. It's necessary for complete combustion. All right. We want to minimize it as much we can, but we got to have it. So it's a necessity. All right. Couple things they're not asking about as much anymore are primary and secondary air. All right. Primary air is air that we supply to the burner with the fuel that controls the rate of combustion, as well as the amount of fuel that can be burned. Secondary air is air supplied to the combustion process that controls combustion efficiency, how completely the fuel is burned. All right. Now, for third engineers, first firemen, they're likely to ask you about tertiary air, and overfire air. Typically, they don't ask second firemen, but let me give you an example. When you have a fuel that's difficult to burn, and I'm talking any solid fuel like coal or trash, part of the problem is this. We put the trash in the boiler, in the furnace, and we hope that it burns in suspension. However, because it's a difficult fuel, some of it often lands on this traveling grate, which is moving pretty slowly in this direction. When it gets to the end, what's on the grate dumps into an ash hopper where we collect the ash. In trash plants, to make sure that this unburned fuel has an opportunity to burn, they often introduce tertiary air under the grate to make sure that we get complete combustion before this dumps off into the ash hopper. All right. The object of the game is to burn the fuel completely. All right. I think everybody understands the concept of overfire air. If this was the combustion process here, any air that I introduce up here will assist in getting complete combustion. All right. So typically what they say in most combustion processes, right here, the fuel is burning to CO, and the addition of that overfire air allows that fuel to burn completely to CO2. All right, does this make sense? Now, they won't beat up a second fireman on this because you haven't been in the industry, but this is a favorite question for first fireman, third engineers. All right, especially if you're a veteran of a trash plant. And
So
those
does that, sorry, I just have a question about that tertiary air.
Yep.
Does that start right away, like on the grate, or do they try to burn it first normally, and then, you know, say the last third of that moving grate, is that when they put the air in, they add the air, or is it adding the air the whole way?
Yeah, typically it's being entered the entire length of the grate because they're unsure because the fuel is so inconsistent. All right, think about it. Yeah, you know, you get a load of fish heads, right? They get thrown in the furnace, you know, you don't know what the hell's going to happen. Or they might be Christmas trees, you know, or something that burns real fast, you know. That's it. They never know the consistency of it. Now, some facilities like CMAS, they'll shred up the garbage and try to get it to burn in suspension. Other plants called mass burn plants start right out by dumping the fuel right onto the grate. All right. So there's different technologies and different types of plants, but basically this sums up what everybody's trying to do. You know, and again, the person they're likely to beat up on this are the people that are the veterans, people that have worked in trash plants. But it is a question in the database for third engineers. So now, and again, like I said, overfire air typically allows us to get complete combustion. All right, so it just assists us in making sure that complete combustion occurs. Their favorite question on this topic is, what are the combustibles in fuel? What actually burns? All right. And again, you learn this early on in science. All right. The combustibles are carbon, hydrogen, and sulfur. All right. be careful because they'll ask you, what are the combustibles in fuel oil? And then 10 questions later, they'll ask you, what are the combustibles in coal? All right. The combustibles are the same, regardless of what the fuel is. All right. The only difference that you should be aware of in natural gas, the carbon and hydrogen are combined hydrocarbons such as methane and ethane. All right. It's carbon and hydrogen. It's just mixed up in a different proportion. All right. All right. The other thing to remember is this: combustion only takes place when the fuel and the air are at the combustion temperature. So you can have a desk at your house made out of wood, which is basically 100% carbon. All right. The reason it's not burning is that it's not at the combustion temperature. All right. They'll often give you a list of combustibles and they'll put oxygen on the list. Oxygen is not a combustible. Oxygen does not burn. All right. It only supports combustion. All right. Any questions? Not generally part of the combustion section of questions, but a miscellaneous question that's very related to combustion is how much oxygen is in the air we breathe. All right. By volume, it's 20.91%. Close enough that most people say there's 21% oxygen in the air we breathe. Does everybody get that? We kind of like to round things up. All right. So either 20.9 or 21% works. The difference is nitrogen. All right. Now you'll notice that there's two percentages here. The first one, percentage by volume. That's important for second fireman. That's the only thing they'll ask you. For third engineers, they often ask you, what is the percentage by weight? All right. And it's slightly different because oxygen is heavier than nitrogen. All right. So the percentage is slightly skewed with 23%, 23.15% oxygen. All right. That's for pure air. As you know, the air you and I breathe, not exactly pure. All right. Contains carbon dioxide, ozone, water vapor, dust, other pollutants. All right. But for all practical purposes, that's what they're looking for when they ask you how much oxygen in the air we breathe. Any questions? Nitrogen, obviously, about 80% of the air we breathe contains nitrogen. All right. Nitrogen is what they call an inert gas. It is not used in the combustion process. Part of the problem in conventional combustion is we introduce air to get the oxygen we need to burn the fuel, and the nitrogen comes along for the ride. It heats up and it goes out the stack, resulting in the biggest heat loss in any boiler, the heat that goes out the stack. All right. Now, there's one kind of sinister side to nitrogen, all right, in the combustion process. At temperatures right around 2,300 degrees, which coincidentally is the temperature that most combustion takes place at, oxygen and nitrogen in the air we breathe disassociate. They come apart, all right, due to the temperature. But as those gases cool, they try to reformulate, but they never get it right. All right. They don't always combine in the right combination. So what we end up with are what they call oxides of nitrogen. You can get NO, NO2, NO3, N2O. You get the idea. Collectively, these things are known as NOx. It is the number one criteria pollutant in the United States. All right. Causes smog, basically ground level ozone. All right. They're not going to beat Second Fireman up at all on NOx. All right. There are no questions in the database. They don't expect that you'll know anything about it until you get in the business and start working. However, for third engineers, if your plant is doing something for to lower the NOx, all right, if you work at a gas turbine plant, that might be SCRs. In a small boiler plant, it'll be burner modifications, low excess air. All right. Be aware of it if it's anything like that is happening at your plant. All right. All right. So the accepted technologies for reducing NOx fall into two categories. We let it happen, and then we deal with it after post-combustion, or we try to prevent it from happening in combustion controls. In power plants, the biggest one today is what they call SCRs, selective catalytic reduction. All right. That's where they let NOx form and then they remove it before it leaves the stack. All right. That's pretty common today. And it works on exactly the same principle as the catalytic converter in your car. All right. All right. Does anybody work in a plant where they're worried about NOx emissions?
Yep,
Who's that?
me, I do. Danny,
Danny, what are they doing for it?
we have an SCR unit.
Excellent. And you're familiar with how that works?
Yep.
All right, good. All right. We won't bore everybody else with the details, but they're likely to ask you specifically during the oral part of the exam how that whole process works. All right. Because you live in Massachusetts, sulfur is no longer a big issue. The state of Massachusetts has regulated sulfur out of anything we burn. That includes gasoline, diesel fuel. If you've ever pumped your own gas, you can see there's stickers all over the gas pumps that we have the minimum amount allowed by law, all right, of sulfur. So sulfur emissions, not a big deal anymore in Massachusetts, all right? Sulfur, when it burns, most of it burns to SO2, sulfur dioxide. When it mixes with water vapor, it causes acid rain, all right? And that has pretty serious environmental impacts, all right? So people that work in trash plants are the only people that have to worry about sulfur, because when you burn garbage, the biggest component of garbage today is the packaging, and most of the plastic packaging, all right, for foods, prepared foods and whatnot, is petroleum products. And petroleum contains sulfur. All right. So only the trash plants really are dealing with it. And most of them use what they call flue gas scrubbers. The flue gas goes into a separate tank, if you will. They spray a lime solution into the flue gas, and that calcium carbonate, the component of lime, absorbs the sulfur. All right. And what comes out the stack is, for most part, sulfur free. All right. So it's costly, but it's effective at reducing. All right. So again, since the only people that worry about it around here today are the trash plants, they don't make it a big part of the second fireman's exam. All right. Does anybody still work at a trash plant out there? No. Danny, you did, right?
Yes, that's correct.
And they had flue gas scrubbers, right?
Yep, we had an atomizing unit for each boiler that sprayed lime to neutralize the sulfur.
Yeah. That's a blast to work with, that stuff, right?
Yep.
Yeah, how they get the lime to work, they water it, they mix it with water and make a slurry. And yeah, they atomize it and spray it into the flue gas.
Yeah, all it looked like was it looked like milkshake once it was all mixed together.
Yeah, yep. Pretty messy as well, right?
Yep.
If you were assigned that duty, you weren't happy. I don't think there's any way you can do that job and not get that lime all over you, but
Especially when the hoses would break and it would start spraying all over the place.
yeah, that sounds like fun. All right. Now, just a couple things that might come up on the test. All right. Everybody here knows that we already mentioned it. The combustibles in fuel, one of the big ones is carbon. All right. When you burn carbon, you're going to produce heat. All right. The other things that you produce exclusively are either carbon monoxide, CO, and carbon dioxide, CO2. All right. Even though it's not great for the environment, what's desirable for us in the combustion process is to produce the highest possible amount of CO2. All right. We don't want to produce any CO. All right. The reality is carbon dioxide and carbon monoxide, either one of them will kill you pretty quickly. All right. But the point is this: when you burn carbon completely to CO2, you liberate about 14,500 BTUs. If you burn it incompletely to CO, you only get about 4,000 BTUs. All right. So there's a big economic penalty as well for not burning carbon completely. All right. The best fuel we have right now on planet Earth is hydrogen. Hydrogen burns completely free of any pollutants, any adverse effect on the environment. All right. The only downside to burning hydrogen is that when you burn it, it combines with oxygen to form H2O, water vapor. All right. The good news is when you burn hydrogen, it has about 62,000 BTUs per pound. All right. So this stuff is literally rocket fuel. All right. This is the best we can get right now. Why don't we burn hydrogen in everything? The answer should be pretty obvious to you: the cost. right now, the cost of hydrogen is about $100-something a gallon, the equivalent price. So even gasoline at $5 is a bargain. All right. Now, one of the questions that they typically ask is this: out of the three combustibles in any fuel, which two have the highest BTU content? All right. So it should be obvious to you by looking at this that hydrogen and carbon have the highest BTU content. Sulfur is a distant third. It's got about 4,000 BTUs. Not a lot of heating value, but still some. It burns and it produces heat. All right. At the bottom of the page is the question they're most likely to ask second firemen. What three conditions are necessary for complete combustion? And what they're looking for are the three T's: time, temperature, and turbulence. You need enough time for combustion to occur. You need sufficient temperature, both the air and the fuel, and you need enough turbulence to get thorough mixing between the air and the fuel. The three T's. All right. Any questions? Now, there are some random questions in the database where they'll ask you, SO2 is produced by burning what?
Sulfur dioxide.
No, sulfur, period.
Oh, sulfur,
Right.
yeah.
Yeah, sulfur dioxide is the end result, all right? Or they ask the same thing about CO2, all right?
Okay.
Burning which combustible results in CO2. So that's the only association I need you to make here. Burning carbon gets you CO or CO2. Hydrogen produces water vapor, H2O. And sulfur gets you SO2 or SO3. All right. Now, this page really has only limited value to the second fireman, but it's showing you the mathematics of this, of the whole combustion process. All right. Remember, the only thing that we need from air in the combustion process is the oxygen component. All right. Nitrogen brings nothing to the party. It's an inert gas. All right. So to burn 1 pound of carbon, we need 2.67 pounds of oxygen. But to get 2.67 pounds of oxygen, we have to introduce 11.53 pounds of air to get enough oxygen to burn the carbon. All right. For hydrogen, it's even worse. I need 8 pounds of oxygen to burn 1 pound of hydrogen. To get that much oxygen, I have to introduce 34.5 pounds of air. All right. So you get the idea. As you go through each combustible, you can see how much oxygen and how much air I need. Here's the number I want you to write down. For the average fuel, meaning natural gas, fuel oil, I need 13 to 15 pounds of air for every pound of fuel I burn. Trash plants are even worse. They require more than 20 pounds of air per pound of fuel. So you need a ton of air to burn fuel. That's the bottom line. At the bottom of this page is perhaps the most useful thing, or the thing they're most likely to ask second firemen. In any combustion process, what I want is best remembered by the acronym high, low, no. I want high CO2. I want low O2. And I want no CO. High, low, no. All right. They have not a whole bunch, but a few questions in the database related to this. All right. If they ask you a high CO2 reading in the combustion process is a good indication of blank, what would you say to that?
Complete combustion.
Very good. Complete or high combustion efficiency. All right. Low CO2 would be the opposite, right?
Right.
So, or if I had high O2 in the combustion process, that's not desirable. That's poor combustion efficiency. Or if I had the presence of CO, all right, again, poor combustion efficiency. All right. So just remember that high, low, no. It'll get you through most of those questions. Now, just above that, there's something they're never going to ask second firemen. All right. This theoretical amount of air formula tells us that we can calculate how much air it takes to theoretically burn any fuel. And right below that is a famous formula known as Dulong's formula that allows us to calculate the heating value of any fuel, how many BTUs per pound, all right, based on analysis. And what that means is we send the fuel sample out to the lab. They send it back and say, your fuel has X amount percentage of carbon, this amount percentage of hydrogen, and this percentage of sulfur. All right. Plug in the numbers and we can calculate the heating value of that fuel. All right. Today, that's done automatically at the laboratory. So they'll give you a printout of it. So you and I really don't have to calculate this anymore. All right. But they'll ask a third engineer, what is Dulong's formula? All right. Second fireman, you don't have to worry about this at all right now. Any questions? All right. Some of the things they ask seem pretty shaky to me. One of the things they ask second firemen is this: how much excess air do you need to burn coal? All right. Now, what I want you to understand is this: what kind of fuel is coal?
A solid fuel.
A solid fuel.
Yeah.
All right. And that's what I want to stick in your mind. Anything that's solid is the most difficult to burn. It requires the greatest amount of air. Does everybody kind of buy into this? All right. Garbage is a whole different creature. It requires a ton of excess air. On the state exam, to burn coal, the state wants you to say you need 30% excess air. All right. Fuel oil, which is a liquid fuel, all right, is easier to burn than a solid fuel. The one drawback to burning liquid fuels is that it has to be atomized. All right. And by the word atomized, I mean the liquid has to be broken up into tiny little droplets of fine spray so that it can mix readily with air to burn it completely. So liquid fuels have to be atomized. All right. They require less excess air, 10 to 15%, than solid fuels like coal. The fuel that's easiest to burn is natural gas. What form is that in?
It's already
It's already a gas. All right. Excellent. So it mixes readily with air. As a result, natural gas requires the least amount of excess air. Does that make sense? All right. So make that correlation, because I'm not sure how they'll ask that. But remember, solid fuels, the most difficult to burn, require the most air. Gaseous fuels are the easiest to burn and require the least amount of excess air. All right. Now, one thing about carbon, all right. Both coal and fuel oil contain relatively high amounts of carbon. The problem with carbon is this: 100% carbon, all right, is very hard. In fact, the one thing that you and I know about that's made out of 100% carbon is what?
Lead? Diamonds.
Diamonds. Excellent. Who said that?
I did.
Now be careful. Never throw your girlfriend's diamond ring in the fireplace. It's 100% carbon and it will burn. All right. Does everybody kind of get that? All right. But coal that contains high amounts of carbon is known as anthracite coal. It's so hard that we can't pulverize it. We have to burn it on a traveling grate. It can't be crushed up because it's harder than the equipment that we use to pulverize it, right? Typically, most fuel oils contain carbon values around 80%. All right. Natural gas contains the least amount of carbon. As a result, when you burn natural gas, you get the lowest CO2 reading. All right. The point I'm trying to make is this: the CO2 reading that you get burning a fuel is completely dependent upon how much carbon the fuel has. Does that make sense? Now they have one trick question kind of related to this on the state exam. If I told you I had 1 pound of carbon and I burned it perfectly using only the theoretical amount of air, what would be my CO2 reading?
0.
Not bad, Martin. It's incorrect. But what would be 0 would be the O2 reading.
Oh, that's right. Okay.
All right. What would the CO2 reading be?
100%.
100.
Ooh, 100%, but only 100% of what?
1 pound.
No,
No?
20.9%.
Oh,
Does everybody get that?
of the air?
If I bring in just enough air to burn this perfectly, means I have no excess air. All right, I would have 0% oxygen going out the chimney,
Hmm.
but my CO2 reading would be 20.9%.
That's because that's the amount of oxygen that's contained in the air we breathe.
Excellent. And I didn't have any extra here. All right. So all that oxygen would combine with the carbon to form CO2. All right. Everybody kind of gets it. All right. Now, in the same kind of vein, same way of thinking, all right. The good O2 values for coal, I would expect to see 3 to 5% coming out my stack when I burn coal. All right. By the way, one thing you might want to write down, 3% O2 reading in the flue gas is about 15% excess air. All right. Fuel oil, about 3%. Natural gas, I can burn that with the least amount of excess air. All right. Because it's a gaseous fuel and it mixes readily with air. It burns quite nicely. All right. With the minimum amount. All right. Now, one of the things that most people have a little trouble buying into is this. If I had two identical boilers side by side, this guy burns natural gas. This guy burns oil. Which boiler would be more efficient?
Gas.
Yes.
The oil-fired boiler would be about 84% efficient. The natural gas-fired boiler would be about 80%. Why, you say?
Because
All right. What's that?
Because of the higher carbons,
No, the higher hydrogen content.
hydrogen.
When you burn hydrogen, what's one of the byproducts?
Vapor, hydrogen vapor, water.
H2O,
Yeah.
baby, water vapor. Let me ask you this. You ever been at a traffic light and you look at the car in front of you and his exhaust pipe and you see water coming out of there? Gasoline has a very high hydrocarbon content. All right. It produces a ton of water vapor. All right. Guess what doesn't burn?
Water.
Water.
Right.
All right. Good thing for us. We would have burnt it up all by now. And so natural gas is less efficient than oil. That being said, understand that natural gas comes directly to the boiler in a pipe. There's nothing for me and you to do. All right. Fuel oil, I have to get a delivery into an oil tank. I got to pump it, all right, to the boiler. I got to clean strainers, burners, all right. I got to blow soot. It's a dirty fuel, but it's more efficient, primarily due to its low hydrogen content and much higher carbon content. All right. All right. As far as efficiency goes, the only question they're going to ask second fireman is how do you calculate the efficiency of anything? All right. And the only thing a second fireman needs to know for the state exam is that the efficiency of anything is the output divided by the input. The only trick here is that you have to have common units. So in other words, the output of a boiler is best expressed by steam in pounds per hour. However, I can easily convert that to BTUs. All right. The fuel input for the boiler is the actual input, and that can be expressed as BTUs per hour input. Does everybody get how this works? All right. I can't divide apples by oranges, but as long as I have like units, the math works. All right. For third engineers, they expect you to understand that in boilers, all right, if I take the pounds of steam per hour and multiply it by the BTUs in each pound of steam, I would get the boiler output in BTUs per hour. Does that make sense? But what you have to remember is this. I'm going to add heat to the feed water outside the boiler. The idea being the hotter I can make the water going into the boiler, the more efficient the boiler process will be. So for that reason, I have to subtract the BTUs that I add to the feed water to do this calculation. All right. In fact, this calculation at the bottom of the page is the math problem that comes right off the third engineer's exam, where they ask you to calculate boiler efficiency. All right. You can see they tell us that the boiler makes 50,000 pounds an hour. There are 1,200 BTUs in each pound of steam. From that, I'm going to subtract 178 BTUs per pound. That's the enthalpy of the entering feed water. Can anybody tell me how I got that number, 178?
Team table.
A good answer. I don't need the steam tables. I took the 210 degrees and I subtracted 32. Remember we went through that exercise, right? If I subtract 32, it tells me the enthalpy in BTUs per pound of entering feed water. All right. So yeah, you could do the steam tables, but I can do it in my head just as quickly. And you can see the boiler efficiency in this problem is 78.14%. All right. When you look at that and you say, oh, that's kind of shitty. All right. Any idea the efficiency of your typical automobile? Gasoline powered automobile? About 30%. All right. So yeah, boilers are pretty good in terms of efficiency. All right. Anyway, where this is going, that's all second firemen need to remember. Output divided by input. For third engineers, this method is what they call a formula, a mathematical formula. It's one of the ways to determine boiler efficiency. The second way is to measure all the losses. Where does the heat go in a boiler? The only thing they're going to ask second firemen, what's the biggest heat loss in any boiler? All right, you already know that, right? The heat loss out the stack. Generally speaking, That's about 10% of the heat available in the fuel. Third engineers, the remaining items on this list are the 7 heat losses that occur in every boiler. All right. So every boiler, from the little home heating boiler to the biggest utility manufacturing boilers, have these 7 losses. All right. That list, third engineers need to know. All right. That's one of the questions for them on the database. What are the 7 heat losses in a boiler? That's the second method. All right. Back in the olden days, they would actually do a controlled test, and they would measure each of these line items in a test they called a boiler heat balance. All right. Today, we don't do that anymore. Today, we take the path of least resistance. What everybody's doing today is using flue gas analysis to determine boiler efficiency. It's calculated by a computer automatically for us. All right. Back in the day, before they had electronics, there was handheld equipment that we used to pull in a sample of flue gas, put it into different chambers that mixed it with a reagent or a chemical to absorb a particular gas. All right. If you've ever watched an oil burner technician, all right, they come and work on your home burner, they still carry these things called Fireman analyzers. All right. They take a hose, stick it into the flue, put this cap onto this cylinder, and pump a sample of flue gas into this device. The chemical, called a reagent, absorbs a particular gas and gives you a reading in the flue gas. All right. You then plug that number into a slide rule, and it basically tells you boiler efficiency. All right. These things are relatively accurate, but they've been replaced today by electronic gas analyzers. All right. Today, many boilers, such as Cleaver Brooks fire tube boilers, have these built in, all right, right on that control panel. All right. So at any given moment, you can read things like combustion efficiency, outside air temperature, stack temperature, anything that you want. All right. Does anybody have any equipment like this on their boilers?
Yeah,
Pretty nice, right? Gives you a snapshot of how your boiler is doing at any given moment. All right. Today, this equipment is required in moderately sized plants. Eventually, it'll be required in all plants. All right. But the key is the information goes to some computers, generally in the control room. All right. For use by the plant operators, but eventually to the DEP. That's the Department of Environmental Protection here in Massachusetts, where they can keep an eye on you as well. Make sure you're being a good neighbor and doing all the right things. All right. So for third engineers, they're going to ask you, can you name 3 ways to calculate boiler efficiency? The first way is by mathematical formula. The second method is by a boiler heat balance. And the third method is by flue gas analysis. All right. By far, the most popular and easiest one today is flue gas analysis. No involvement from me and you. All right. And that's what we like, right? Now, wasn't that long ago that, in fact, I'll tell you exactly, 10 years ago, almost to the day, is when I updated this page. And at that time, over 50% of the electricity that we generated in this country was by coal. All right. Guess what percentage is by coal today in New England?
30?
0.
0. Oh, New England. I thought you meant the country.
Yeah, in the United States, it's down around 32% and it's dropping fast. All right. That's good news for you because they've eliminated most of the coal questions from the state exam. All right. Yeah, and that's only fair, right? We're not burning any coal. All right. I think New Hampshire, that place in Bow, New Hampshire, still open. They still burn a little coal up there in New Hampshire, but I don't think that's long for this life. Now, what do they ask about coal still today? How many people have heard the term spontaneous combustion?
Yep.
What does it mean, Martin?
It just, without an ignition source, she lights off.
Okay. And what substances did that typically happen to?
Humans, chemicals in air.
Chemicals, dust.
Actually, what I was looking for was any carbon-based substance. All right. The big cool classes of spontaneous combustion happen at like grain silos. All right. Sugar factories. But it's a big problem with coal. And Martin's exactly right. Spontaneous combustion is defined as the combustion of a substance without an external ignition source. Right. Obviously, in a coal plant, if the coal burns outside the boiler, it's a disaster. Does everybody get that? All right. Yeah, typically it's out in the yard, all right, in a pile, and the coal's burning. That's bad news. All right. The one way they prevent that is they continuously move the pile, they spray water on it. All right. But it's a big deal. So one of the questions still in the database for second fireman is, what is spontaneous combustion? All right. This single line diagram is in there just so everybody gets it. All right. Around here, the coal is stored in giant piles outside where it's subjected to the weather, and rain and snow and wind even deteriorate the coal pile. All right. So, it's kind of a bad thing. The point here is this: I need conveyor belts to get the coal from outside into the plant where I put it in silos. A feeder supplies the coal to a pulverizer where it gets crushed up to the consistency of baby powder, mixed with heated air and blown into the boiler. Because coal is a pretty dirty fuel, we require a lot of back-end equipment, all right, to control the emissions from the plant. So there'll be ways to control particulate, ash, there'll be scrubbers, SCRs, all kinds of equipment. Here's what you need to know. Coal is dirt cheap, all right? It hasn't changed much in 50 years, the price. What's changed is all the equipment the plant has to have to make it comply with environmental regulations. All right. So to give you an idea, when I retired from Brayton Point, it was costing us about $35 to make a megawatt of electricity. Natural gas plant was making it for 18. All right. Because they didn't require nearly as much back-end equipment. The other thing I just want you to grasp about coal is this. You can't get a pickup truck full of it or a tractor trailer, all right? You need mass quantities of it. At Brayton Point, we got 40,000 tons delivered every 3 days, all right? And the only way we could get it there was by a ship. All right. So this shows you the unloading process. You know, it would take about 8 hours to unload the ship. And then it would go back to Newport News, get more coal, and then come back, you know, week in, week out. All right. You get the idea. All right. They won't ask you anything about this. This is just for your own information. The other alternative to this are coal trains. If you've been in other parts of the country, you know, places I've seen of Florida, Nevada, they have huge trains, you know, a couple hundred cars long, delivering coal to these coal burning plants. Now, one of the technologies they used in coal was a technique called tangential firing or tangential burners. And in these burners, the actual burner nozzle is in the corner of the boiler. Remember, the pulverized coal crushed up, mixed with air, and blown, literally blown into the furnace through pipes, all right? Because it was traveling at high velocity, if that fuel hit the walls of the boiler, it would be like sandblasting, and it would have an erosion effect on the boiler surfaces. So what they did, they come up with this tangential firing to keep the fireball, the fuel, in the center of the furnace away from the walls. All right. So one of the questions in the database is, what is tangential firing? All right. It is firing from the corners of the furnace. All right. But more importantly, I think the other question related to this is, what is flame impingement? Flame impingement is when the fire, the flame, actually touches the burner walls, the furnace walls. That's considered detrimental. All right. One, it leaves deposits on the burner walls. All right, the furnace walls, and it leads to erosion of the tubes. All right, and it results in incomplete combustion. So the question you're more likely to see for second fireman is, what is flame impingement? And that's when the flame touches the boiler surfaces. I think I stuck a couple other shots in of tangential firing. You probably don't have this picture, but it's just a better picture showing you what's going on. And this shows you a single line diagram of actually one of the boilers at Brayton Point that had not only tangential firing, but they had what they called a split or divided furnace. All right. You can see the pulverizer, the coal pipes, and how the fuel got distributed to the various levels in the boiler. Way back when we talked about controlling superheat temperature, I told you that one of the techniques they used was tilting burners. All right. And probably most of you will never see, this is an actual burner from an coal-fired plant. But the concept of tilting burners, you can see right here. All right. I could tilt the burners away from the superheater to help me control the temperature. Or conversely, I could tilt the burners up to get more superheat temperature. All right. So these burners typically had a range of about plus or minus 30%, where they could tilt up or tilt down as needed.
So you could move them in the field.
Well, you could move them from the control room, but you could also manually move them locally by a hand wheel, but they were hooked up pneumatically at Brayton Point. So, air pressure could manipulate them or position them. They looked more like this, but this whole assembly would tilt up and down. But again, I don't think they're going to beat you up on any of this stuff. This is just for your own knowledge. But in a coal plant, what they'd do, they'd take the fuel, crush it up in a pulverizer, and add heated air, and then that mixture would go to the burner. All right, and then they'd provide over fire air to get complete combustion. All right. A little bit different than conventional combustion process. A pulverizer was just a big machine with basically 3 big wheels that spun around. The coal would be fed in. It would get crushed up by these wheels. The heated primary air would pick it up, try to pass it through a screen that had a pretty tight mesh and called a classifier. And if the coal didn't pass through the classifier, it fell back in, got crushed up a little more until the pieces would fit through the classifier. All right. But again, it was like the consistency of baby powder. It was crushed up pretty fine. They used to ask third engineers, can you name 3 types of pulverizers? There was an impact mill, there was a bowl mill, and my favorite was the ball tube mill. This thing was a big metal tube filled with baseball-sized steel balls that rotated around. The coal was blown in there, and it would get crushed by these little steel balls. All right, pretty primitive. In fact, what they say, most coal technology, I mean, we hadn't had any improvements since the 1940s. We're still doing it the same way. All right, there's nothing to improve upon. But this shows you that coal would be put in a silo inside the plant. It would feed by gravity to a coal feeder. The coal feeder would provide the pulverizer, and the coal pipes would deliver the fuel to the burners. ultimately to the boiler. All right. Some graphics showing you how you control the combustion process. This is a picture of a pulverizer with the exhauster, lube oil pumps, and all that stuff, the related equipment. None of that's important. They're not going to beat you up on this. One of the interesting things, how they burn the hard coals, the anthracite coals, throughout the rest of the country is on these chain grate stokers. All right. This is the technology they use to burn trash today. All right. For instance, at a plant like CMAS, they would blow the garbage in. It would try to burn in suspension, but it would end up on the traveling grate. And again, this thing rotated pretty slowly, dumping off the ash at the end into an ash hopper. But they would deliver air underneath the grate, that tertiary air, to get this fuel to burn completely. All right. These things are a maintenance nightmare, as you can imagine. They're exposed to the high temperature of combustion. They're made out of metal, so something's going to give eventually. A coal feeder, real simple device. Gravity fed the coal onto a belt. Equipment made the coal a uniform height, and what you controlled was the speed of the belt. You could make it go faster or slower, dump the coal into the pulverizer, and ultimately into the boiler. Now, the other thing that they asked second firemen, kind of related to coal, but it could be related to trash as well, or oil, is slagging. All right. Most people know that slag in a boiler is the molten ash that adheres to boiler surfaces. All right. When the boiler is hot, this isn't a big deal. All right. However, as you can imagine, what happens to that molten ash when the boiler cools down? That ash, yeah, it becomes very hard, like concrete. All right. And somebody's got to remove it. All right. That's not a fun job. All right.
You jackhammer for hours.
Is that right?
Yep.
Yeah, that job sucked, huh?
I had to do it many times. It really did suck.
Yeah, when they hand you a jackhammer in any job, you know that's not what you signed up for. But all right. But everybody gets slag, right? So they'll ask you, what is slagging in a boiler? And it's just molten ash adhering to boiler surfaces. All right. Becomes a real issue because to get in the boiler, you have to cool it. Once the ash gets cool, it gets hard like cement. And as Danny says, when they hand you a jackhammer, that's good luck. All right. This is obviously detrimental to boiler operation. And the slag typically gets on the tubes in very hard to access locations. All right. Everybody kind of gets this. So yeah, cleaning it is not as simple as whipping a jackhammer on it. All right. The other term that comes from the coal industry is spalling. So slagging and spalling kind of go hand in hand. But what happens is that molten ash sticks to the boiler surfaces. It gets cool. All right. And it gets heavy. And as it falls off, it has a tendency to pull refractory material off the boiler walls. All right. Where it happens a lot is right around the burners. All right. And what you end up having to do pretty much every overhaul is go in there and patch, with refractory cement, the area around the burners because it's been deteriorated by spalling. Everybody kind of get this? All right. As that heavy molten ash falls off, it pulls that refractory material off with it. Any questions? So even though there's a lot of shit about coal, they've eliminated most of the questions. So again, spontaneous combustion, flame impingement, tangential firing, maybe tilting burners, slagging, spalling. Expect to see those type of questions on the state exam. But for everything that's happening with coal, it's really not a lot to remember. Any questions? All right, before we get into fuel oil and natural gas, why don't we take a break? It's about halfway time, right? Yeah. Yeah, all right, I'll see you in about 10 minutes or so.
Three.
Billy.
Won't let me do it by phone. Well, Thursday night, Mom's gone. This Thursday. You don't decorate ever, you decorate like a hundred.
And so, what? I have a great relationship. I have a great relationship.
Hello, looks like we're back at it. Sure, I got everybody here. All right, now, obviously, they're not going to ask you a lot about coal, and because natural gas is so simple to burn, the majority of the combustion questions are going to be about burning fuel oil. All right. There's about 5 definitions kind of associated with fuel oil. The first one we've already talked about, specific gravity. Remember when we talked about specific gravity, we said that it was the weight of any substance when compared to the weight of water. Water, 8.33 pounds per gallon. All right. In this industry, that applies specifically to fuel oil. All right. All fuel oil that gets delivered to us has to have a specific gravity less than 1. All right. That way there, if they spill it, particularly in the ocean, it'll float on water. All right. If you've ever worked in a plant that burns fuel oil, the way they express specific gravity of fuel oil is by what they call API gravity, or 8 degrees of an API. API is a scale from the American Petroleum Institute. All right. And all that is unimportant to second fireman. The only thing that comes up, all right, as a math question for second fireman, first fireman, and third engineers is this. If they tell you the specific gravity of any particular fuel, and let's just pick 0.89 is what they have on the test as the specific gravity, they're going to ask you, how much does a gallon of that fuel oil weigh? And what they're asking you to do is take the known weight of water and multiply it by the specific gravity of 0.89. And that will give you the weight of the water per gallon. All right, does everybody kind of get this? All right, it's pretty simple math. All right, that's the only thing that comes up about specific gravity. All right. At the bottom of the page here is the other question they love to ask about oil. How many gallons in a barrel of oil? All right. Now, they're going to try to trick you on this, and that question, they'll put 55 gallons. If anybody's ever worked in a factory where they have drums of stuff, 55-gallon drum is a pretty common size. All right. What happened in this country, 1859, the guy that discovered oil on his property was in the molasses business. The barrel he had laying around was a wooden barrel, 42-gallon, used for molasses. He stuck the oil in those molasses barrels, and that became the standard in this country. All right. So today, when you hear the price of oil, they're talking 42 US gallons. All right. Occasionally, they'll ask you how many BTUs in a gallon of number 6 oil. All right, 150,000. And how many BTUs in a pound of 6 oil? 18,750. All right. But that's about all they'll ask until you get to these 4 definitions: viscosity, flash point, fire point, and pour point. All right. Viscosity for second fireman is pretty simple. All right. All they're looking for is the first line. All right. Viscosity is defined as the internal resistance of fuel oil to flow. All right. Probably that thing that makes that easiest to remember is the second sentence where it says heating fuel oil will lower its viscosity. All right. So heating fuel oil makes it flow easily. All right. Does everybody kind of get that? All right. Now, third engineer is where they're going to go off on a tangent on you, and they're going to ask you a little bit more about viscosity. All right. And first of all, you should understand that it's measured in 2 scales, SSU and SSF. SSF stands for Seybold seconds Fural. SSU, Seybold seconds universal. SSU is for light oils. SSF is for heavier oils. All right. The machine that measures viscosity is called a viscometer. All right. And while it looks pretty technical and amazing, what a viscometer actually does, it heats the oil up. So it passes through an orifice all right, and fills, what they're actually measuring is how many seconds it takes to fill a 60 cc container with oil, all right? Why is all this important? The burner manufacturers, the oil burner manufacturers specify what viscosity you should have at the burner tip to get complete combustion. So that's why this whole viscosity thing comes up. In large plants, generally utility plants, a viscometer is required on the fuel oil supply to the burners. So it has to, have that equipment specifically in the plant. So they'll ask about viscosity for all levels. They'll ask about flash point. All right. Flash point is pretty simple to define. It's the temperature that an oil will ignite with a pop, but not continue to burn. All right. The guideline we use in this business is that we preheat fuel oil, particularly number 6 oil, to within 10 degrees of the flash point. That's the proper preheat temperature. All right. If anybody's wondering what that is, it's around 180 degrees. So that's a question specifically on the test. At what temperature do we preheat the oil? All right. And that's so we can pump the oil from the storage tanks to the boiler and atomize it properly. The fire point is really not a concern of you and me. Fire point is more a concern of the people that work in refineries. All right. Fire point, pretty obvious. That's the temperature at which an oil will ignite and continue to burn. All right. So when these guys are pumping product around the refinery, they got to be careful that it doesn't reach the fire point. All right. Or the stuff will catch on fire. And, without exception, every year you hear of a pretty good refinery fire somewhere down south. And typically what happened, they weren't paying attention. They preheated the product to the point where a fire started. And the other thing that's important around here is pour point. All right. Number 6 oil has a pretty high pour point. All right. In other words, 6 oil has to be about 90 degrees Fahrenheit for it to flow easily off the truck. If it gets below that, it gets like molasses and it won't come off. It won't come off the truck. All right. Pour point is defined as the lowest temperature at which an oil will still flow. All right. And obviously, when you think about it, what happens is this: the truck driver takes his tank truck to the terminal, fills up with oil, which is typically preheated to 110 or 120 degrees. His truck is like a big thermos bottle. All right. And he drives around. If he comes directly to your plant, no problem. If he gets waylaid, there's a traffic jam, stops at his girlfriend's house, whatever. All right. The oil cools. If it cools enough, it won't come off the truck. So pour point is an issue in New England because it does get cold. Everybody kind of gets that, right? So flash point, fire point, and pour point are the definitions they typically ask about oil for second firemen. Right. Now, every now and then they got random questions about oil storage tanks. All right. Obviously, you need a tank to keep oil in. All right. You just can't pour it in any container. All right. Above ground tanks are the norm today. If you have below ground tanks, underground tanks, all right, they passed law about 20 years ago that says you now have to have secondary containment and monitoring equipment on those tanks. So that those tanks were kind of grandfathered in. They let you keep them if you made those modifications. Now, anybody in this business knows one of the tasks that associated with storage tanks is sticking the tank. That's where you take a graduated stick, you go out there, you stick it in the tank, try to determine the level of oil in the tank. All right. Often you have to do that at pretty bizarre times. All right. Many plants want you to do it before you accept an oil delivery. Many plants make you do it after you get an oil delivery. So has anybody ever done this? Sticking the tanks?
Yep.
Yeah, it's not cool. There is remote monitoring equipment that's available, but it's kind of unreliable because fuel oil has one nasty characteristic. As you heat it up, its specific volume increases. All right. So its specific volume changes with temperature. All right. And as a result, you often have to know the temperature of the oil to figure out how much of it you have on hand. Does everybody kind of get that? Many plants have conversion charts that are available for you to calculate. If you got oil at 130 degrees, how much do you have? Does everybody kind of get that? All right. Now, at the very bottom of the page, there's only a couple things they ask about natural gas. One is how many BTUs in a cubic foot? 1 cubic foot of natural gas is about 1,000 BTUs. All right. If you buy natural gas at your house, you pay for it by the therm. A therm is 100,000 BTUs. All right. If you work at a big utility plant or a manufacturing plant, they typically buy natural gas by what they call the decatherm or the MMBTU. Decatherm and MMBTU are 1 million BTUs. All right. Any questions? Now, this chart is really not something they're going to beat you up on, but this is basically what happens. The fuel oil that comes out of the ground is what's commonly referred to as crude oil. All right. Crude oil goes to a refinery and they put it in what they call fracking towers. All right. So the crude oil is heated about 700 degrees, and the vapors that come off of that are condensed, and that becomes number one fuel. You and I know it as gasoline, kerosene, all right, products like that. All right. The next step is they heat that remaining crude oil up to about 950 degrees, and they drive off what we know as number two fuel oil, home heating oil, diesel fuel. All right. What's left over is what they call residual oil, or number six. All right. In the old days, they called this bunker C. All right. Bunker A was number one oil. Bunker B was number two oil. And bunker C was residual oil, or number six. To make number four oil is simply just a blend of equal parts number two and equal parts number six. All right. Number five oil is 2/3 six oil and 1/3 two oil. So 4 and 5 are nothing more than blended fuel oils. All right. You can see the only thing that possibly would be of interest to you is the specific gravity and the weight per gallon. All right. Gasoline weighs about 6.8 pounds a gallon. All right. Number 6 oil, about 8.2 pounds per gallon, a little less than water. All right. Again, number 6 oil is 150,000 BTUs per gallon. Number 2 home heating oil is about 141,000 BTUs per gallon. Can't imagine that'll ever come up. All right. Any questions about this whole thing? They won't beat you up on this, but many people have heard me say number 6 oil. All right. That's the heavy fuel oil that we burn, in utility manufacturing boilers. All right. It's tough to work with. All right.
Hey, Tom, question. Can you explain what that API number is again on that chart?
Yep. The specific gravity is what you and I understand. That's the weight of it compared to water. All right. Per gallon. All right. Does that make sense? All
Yeah.
right. All right. And you can see that how these numbers correlate here. The American Petroleum Institute made up their own scale called API gravity, and it looks like a complicated formula, but it's really not. All right. And here's how it works. 10 API equals 1 specific gravity. All right. And as the numbers increase on the API scale, the specific gravity decreases. All right. All right. So for instance, API gravity of 28 is number 6 oil that has a specific gravity of about 0.9. All right. It's just a scale that they kind of invented on their own. But if you look at the formula itself, the math of this, the 141.5 minus 131.5 always gets you back to the number 10. All right. And 10 in the API scale equals 1 in the specific gravity scale. All right. So yeah, they made it. The American Petroleum Institute just made this up, for a convenience for them. Here's the interesting thing. When you accept a load of oil, the delivery ticket will always have the API gravity on it. All right. That's the number that, they're interested in. You and I could care less. All right. But knowing the API gravity number, all right, we can figure out the heating value of that oil in BTUs per pound. All right. Not that you and I would ever need to do that or want to do that. So it does have some value to somebody. You and I, we don't care. All right. Whether we get 17,000 BTUs or 18,000 BTUs, it doesn't matter. But does that kind of help you?
Yeah, thank you.
Yeah. Don't ever worry about this. Now, specific gravity is something anybody that's bought motor oil has seen before. If you ever look closely at a can of motor oil, if you're going to change your own motor oil, it'll have the specific gravity on it with the number 6060, 60-60. That means they're taking that fuel oil or that motor oil and comparing it to water at 60 degrees Fahrenheit. All right. That's all it means. So many of you buy oil by the weight, like 30 weight oil. All right. That all is related to specific gravity. All right. Now, back in the day, they used to have second firemen draw a single line diagram as part of the oral exam of a fuel oil system. All right. Just so you could understand it. All right. Today, 90% of everybody's burning natural gas, and fuel oil systems are no longer part of the equation. However, they have a question in the database that asks, which of the following components is not part of a fuel oil system? So, as I usually do, I list the things that you need, the components you need to burn fuel oil. All right. You need a fuel oil storage tank. You need pumps to pump the oil from the tank to the boiler, fuel oil strainers, take out any crud in the oil, fuel oil heaters. Typically in this business, they can be either steam or electric heaters to heat up the oil, to preheat the oil to the proper temperature. You'll need pressure gauges and thermometers on the system, so you got a feel for what's going on. All right. But I haven't heard of anybody having to draw this in over 5 years. So, but let me assure you, it's a relatively simple task if they call upon you to do so. All right. If I was asked to draw a fuel oil system, I'd draw a tank, a pump. You get the idea. Some strainers, a fuel oil heater, pressure gauge, thermometer, you get the idea. All right. And every fuel oil system to the boiler will always supply more oil, with the excess being returned to the tank. All right. Many fuel oil systems have valving arrangements that allow them to pump oil through the heater and back to the tank to preheat the oil, to get it warmed up, to get it to the proper temperature. Most fuel oil tanks in New England have steam coils inside the heater, so we can heat the oil that's in the tank. All right, does everybody kind of get this? All right. The only other issue that'll ever come up is that whose responsibility is it when the truck comes to deliver a load of oil? All right. Now, this has gone to court a bunch of times. All right. What they've decided is that it's the plant operators. All right. Once the truck pulls up, puts the hose in your tank, it's your problem now. All right. So most companies are pretty good. If it's a cold February at 2 o'clock in the morning, you don't want to have to stand out there and watch this. So most drivers are pretty good. They'll keep an eye on this operation until they're done. Has anybody ever accepted a fuel oil delivery?
Yeah.
Did you hang out there the whole time, or?
Every time, yeah.
Yeah.
With the driver. Yeah.
Yeah.
Just watching the gauges while he's delivering the fuel oil.
Yeah.
Yeah.
Not pleasant, especially when it's really cold out,
No.
snowing and all that other shit. So, but again, I wouldn't worry too much about this. They haven't asked it in quite a while, but it could be part of the oral exam. All right. So, so
How
that's
long does
why-
it normally, how long does
What's
it
that?
normally take? How long does it normally take to fill it up completely?
Typically it takes about 45 minutes to dump a truck, about 7,000, 8,000 gallons are in a tank truck. And yeah, it's heated. It comes off pretty fast. But yeah, you're out there. Each company will have a different policy. In fact, one of the first things that happened to me at the paper mill was the guys were taking a load of oil. The hose came out or disconnected, whatever. They spilt about 150 gallons of number 6 oil. It was a big deal. You had to call Clean Harbors to come clean it up, and but everybody survived it.
So why would the hose be disconnected if you do it properly?
Yeah, it shouldn't. In fact, most of the connections have like a wire, safety wire. So even if it comes off, it won't fly off. It'll keep it in that general area. Yeah, it shouldn't happen at all. Especially if you're standing there watching it like you're supposed to be, right? But anyway, one of the things that I never liked about oil is this. You burn it in an oil burner gun, and they periodically become fouled or dirty, which means you got to pull the gun out of the boiler, put it in a workbench, and clean it. All right. Cleaning it basically entails taking it apart. And the part that's going to concern you most is the burner tip. All right. It'll come apart. There might be a swirl plate or an atomizing plate behind the nozzle. Throw those components into a bucket of kerosene, safety clean, or whatever you got. Clean them up, reassemble it, hang it on a rack. It's ready to rock and roll, or put it back in the boiler. Today, most oil guns are what they call steam or air atomizing burners. All right. Back in the early days, the early burners were rotary cup burners, and that was known as a mechanical burner. The burner tip actually spun by pressure. All right. And that had a tendency to fling the oil out, break it up into little drops to make it easily mix with air. Today, there are pressure atomizing burners or steam compressed air atomizing burners. These are the most common. However, the question on the state exam is, can you name 3 types of oil burners or 3 ways to atomize fuel oil? All right. And these are them: the rotary cup burners, pressure atomizing, and steam compressed air atomizing. The other weird question they asked second fireman, and I didn't think I needed this diagram till a couple of students come back and said, they asked us a question, we didn't know the answer. All right. And the question was, what's the difference between an outside mixing burner and an inside mixing burner? Well, in the outside mixing burner, the steam and the oil mix beyond the burner tip. In the inside mixing, the steam and the oil mix before the burner tip. All right. Here's the ironic part. No, neither one of these is better than the other. All right. And I mean in every aspect. I originally thought the inside mixing would foul. All right, but I was thinking wrong. It turns out they both get plugged up at the same rate. All right, so there's no preference, I guess, is what I'm trying to tell you. All right. Does everybody agree with me? You think this one would plug up sooner? No? Nobody kind of agrees with me? When I first got to General Motors, I was what they called a boiler operator. And the boiler operator's primary job was to clean oil guns and replace them. Once you got to a second engineer, you had a partner that was a third, and he was the burner guy. So I only had to do it for about 6 months. I'm not an expert on oil burner cleaning. The chief would always catch me cleaning the components, like the burner tip on the grinder. You know how most grinders have that hard wheel and then they got a wire brush? I would use the wire brush part of that on the grinder to clean the components. And I guess that's a no-no, causes them to wear a lot faster. Kept them nice and clean though. In the pressure atomizing burner, typically what happens, they deliver oil to the burner tip at about 30 PSI. The oil goes through a narrow passageway, and what happens? The velocity of the oil increases due to the pressure drop, and it hits a sprayer plate that breaks up the oil into fine droplets, allows it to mix more readily with the air. That's how a pressure atomizing burner works. Again, the only question for second fireman is, can you name 3 types of oil burners?
I got a question on the steam atomizing burner.
Yep.
Does it have to be at a different pressure than the oil feeding it?
Yep. Yeah, what they say, what they want is the steam pressure to be 5 to 10 pounds higher than the
Okay.
oil pressure. That way, if the burner gets a leak in it, in that inner tube, all right,
Yeah.
the oil won't leak into the steam, but rather the steam will leak into the oil. All right.
Okay.
Does it matter? I don't think so.
No.
All right. What typically happens is nothing's returned from the burner. All right. But because of that rule, in the fuel oil heaters, which are nothing more than shell and tube heat exchangers like we talked about, the fuel oil is inside the tubes with the steam outside the tubes. All right. Same thing. You want the steam at a higher pressure. All right. So if one leaks to the other, the steam will leak into the oil rather than the oil leak into the steam, because in some plants, they recover the condensate from the fuel oil heaters,
Okay.
and you don't want that contaminated with oil.
Right.
All right. So at this point, the steam pressure's 5 to 10 pounds higher than the oil pressure, and they maintain that right to the gun. All right.
And you'll know if that fails.
Oh, yeah. Oh, yeah. And yeah, I'm glad you brought that up, because the other point everybody should understand is that they're called steam or air atomizing, because if you have just a single boiler in the plant and you have to start up, you don't have any steam, you can use compressed air. All right. And then when you get enough steam pressure on the boiler, you can switch it over on the fly to steam. So that's pretty typical as well. But I think, oh yeah, natural gas. gets delivered to the burner in a pipe. All right. There are automatic shut-off valves, solenoid valves. All right. Idiot proof. All right. One question I saw recently on the third engineer's exam, if anybody looked at the gas piping next to the boiler, all boilers in Massachusetts have what they call a block and bleed arrangement. Do this. And in that block and bleed arrangement, there are two electrically operated valves, solenoid valves, and a vent valve. This being the vent valve. When these valves open, they open simultaneously. The vent valve closes. When these valves close, the vent valve automatically opens all the time. All right, the idea is if one of these leaks when they're in the closed position, the gas will be vented to the atmosphere, not into the boiler. Does everybody kind of get that?
Mhm.
All right. And so this block and bleed setup is on every gas-fired boiler. So if you're in a boiler room, check it out. Make sure you kind of get it and understand how it works. But it's a requirement in Mass.
There's a
But I
manual,
think that-
I think there's a manual vent valve too, just to. back up.
There is, and there'll be manual isolation valves, so
Yeah,
you can close off the gas. There'll
even on
be-
the vent valve, even on the vent valve, I think there's a manual.
Yeah,
Yeah, to back up, to back it up.
okay. I'll have to take your word for it, you know. In fact, if any of these valves don't do what they're expected to do, you'll get a disagreement in the logic and it won't let you start the boiler. It'll say something's wrong. But I think that's enough for tonight. I think this is where I stopped in the day class. So what I'll do tonight, I'll send you homework number 6. It won't be due till a week from tonight, Monday. I think it's the 28th. Other than that, I'll see you on Wednesday.
All right, have a good night.
All right, good night.
Thank you.
Good night, Tom.
Good night.
Thank you.
Thank you.
this officer. I don't think they've added that. Okay.